So let's go through. Continuity is the start. That's 2.3. I'm just going to go in order. I like the order of the book so far. We pretty much do always go in order of the book. All right, continuity. Let's start off with the definition, which you should know by now. If the limit as x approaches c of f of x is equal to f of c, then f of x is continuous at x equal to c. And I always start off with just that piece for you guys because I want you to be able to know the notation, but I need you to understand you're doing a little more than that. You're actually finding out that it's continuous at a place, at a singular place, the place where you take the limit. So that's the start. When we did this, continuity is common sense also. When you look at a graph, you guys should be able to tell if a function is continuous just by looking at it. That's easy to tell. We're going to go through the 4 types that you guys have. Removable. Okay. A removable discontinuity, those are your little holes. So if I give you an example, and I'm going to make them really easy so that I can remember and know that it works. All right, something like that, right? We know that because it factors and because the factor cancels, then we know that there's a removable discontinuity at x equal to -2. What else did you learn about them? You learned that you could find the y value. Okay? How do you find the y value? You take the simplified version and then you substitute in the value. And you get -4. So the hole, or the removable discontinuity, is exactly at this point. Things that we know about all removables. Every single removable discontinuity has the same few features. Number 1, the limit as x goes to, and I'm just going to write removable discontinuity of f of x, always exists. And what is it? It's that y value we just found a second ago. Happens every single time. Every single time. If I asked you to rewrite this function as a piecewise function to remove the discontinuity, you had that in your notes. We can do that also. I'm going to pause to make sure we're good if I change the page. All right, so I'm going to call it g of x, removing the discontinuity. Well, then g of x would be the same thing as you putting f of x for any place where you're not the discontinuity. I can't remember, -2 or +2? -2, okay. And then put in the y value of the discontinuity right at the discontinuity. That's how we remove it every single time. Every single time. This is the original function. Put a note for yourself. That's the original function you used. Just ignore and then use this one point in its place. Okay? Removing discontinuities. That's the first type of discontinuity. How do you know? Because a factor will cancel. Are we good on that? Okay? You should be able to remove it. You should be able to tell me the y value. You should be able to tell me a limit. And you should be able to tell me a piecewise function. Those are all the things you should be able to do. Okay? Then we have a jump discontinuity. Easy jump discontinuities. Greatest integer function, that would be an easy jump discontinuity. 1 unit over, up 1 unit, to the right 1 unit. That's your easiest jump discontinuity. What are other jump discontinuities? A lot of your piecewise. So, so there's that one. And then I'll do a purple guy. One, two. Alright, so those are my two piecewise functions I'm writing for you, and then the questions I could ask you are, is the function continuous? And then I just say that much, right? So, if I ask you that, can't do it now, come at the end of lunch, okay? Alright, so, if I ask you, is the function continuous? Most of the times, if it's continuous, it's because there isn't a jump. Most of your piecewises, because either they'll meet up perfectly and maybe have a removable discontinuity, or there will be a jump most of the time. I could make it have an asymptote in between. So, how do I know? Because you're going to check the pieces. So, for this piece, I'm only checking at x equal to 1 because that's the break of the function. And at x equal to 1, this one is negative 1. At x equal to 1, this one is positive 1. What did you just find? This guy is the limit as x approaches 1 from the left. This guy is the limit as x approaches 1 from the right. They are not the same. The limit doesn't exist. And if the limit doesn't exist, then it can't be continuous. Why is it a jump? Because this piece jumps to this piece when you graph. You go from negative 1 and you have to jump over to 1. This guy, when you substitute him in, and I'm going to go this way, you get 2, and this one here, you get 2. So these are the same values. The limit from the left is equal to the limit from the right, which is equal to the value at 1, which is also 2. Therefore, it's continuous. No jump discontinuity. Okay? So I'm going to summarize those two things to start. Okay? I'm going to summarize those two things with limits. That's the stuff you guys have some trouble with. So, removable discontinuity, the limit as x goes to c of f of x exists, but the limit as x goes to c of f of x won't be equal to f of c. Definition of continuity. Right? Jump. The limit as x goes to c from the left of f of x does not equal the limit as x goes to c from the right of f of x. But, I'm just going to add this in for you, but both exist. Because I think the way I showed it to you, I called one of them L and I called the other one M, if you look back at your notes. Okay? Limit definitions. You got to know them. Okay? If I call this limit L, and I call this limit here, I got to show it. If I call this limit here L, and I call this limit M, it should make sense to you. That's still a jump, even though it looks different than the definition I wrote. Because one of them has a number, the other one has a number, but they're not the same number. L and M are different. Removable, jump. Are we good? Okay. Let's see. Then we got our infinite, and I'm not going to do too much detail. Infinite discontinuity, that's the same exact thing as a vertical asymptote. And when you do limits, whenever you're asked to do limits, you do a sign chart. We did that together yesterday. And when you do a sign chart, you need x-intercepts and vertical asymptotes. They're the same thing, vertical asymptotes and infinite discontinuity. So, how do you find an infinite discontinuity? Well, using this example, let's say. That would be my simple factoring example. Well, what do we get? X minus 2, x plus 2, x minus 2, x plus 1. This guy is a removable discontinuity because it canceled. This guy is a vertical asymptote, which is the same thing as an infinite discontinuity because it didn't cancel. Little pieces that you guys were getting wrong in 2.3. Any questions on that? We talked really pretty intense in class why we know that once you have an infinite discontinuity, or a vertical asymptote, you know your limits. You know they're going to be positive or negative infinity as long as it's within the domain. That is its definition. Okay? Anyone? Am I missing anything? Have I lost you yet, Samantha? Be careful. The removable discontinuity happens at x equal to 2, because that's what makes this factor 0, and it occurs at 4/3. Is that what you were asking? Oh, the x-intercept. Yes, the x-intercept happens at -2. Yes, -2 comma 0 is the x-intercept. Sorry about that. Anything else? Ty, we're good? We're good? All right. Yeah, sure. All right, what's the only one we're missing? Oscillation. I know. That one's kind of a pain. We talked about it. It's the only example that I can possibly give you right now. You won't see it much at all, but you do need to know that there's 4 of them. There's no limit definition for this guy because it's crazy. The function is absolutely crazy, okay? It does that crazy bouncing, and the more you look at it, it never gets linear. It just keeps bouncing. All right, so those are your 4. Let's do a summary one more time. A function is going to be continuous as long as, or has continuity over every single x value in it, if it doesn't have these guys, discontinuities. And you do need to know all 4. You should be able to give a limit statement for the first 3. You have your removable. You have your infinite. You have your jump. And you have your oscillating. If you are an infinite discontinuity, can you also be a removable discontinuity? They both are at the bottom. They both make the bottom 0. Can you be both? Have you ever drawn both and gotten it right? The answer to that question is no. You can't have both. Therefore, this list is exclusive of each other. Once you are a removable, you cannot be any of the others. Okay? So that is discontinuities. Then, proving continuity. I want to prove that a function is continuous. Well, I could give you a function. Proving continuity. So things I don't want you to get messed up about. Number 1, sometimes the functions are not written in order. I did the greater than first purposely, and then I did the less than second. When you see that, make sure you understand which one's which. The left side is the less than, the right side is the greater than. Okay? So what's the proof? You essentially do 4 things. You do the limit as x goes to whatever that value that you're trying to prove continuity from the left. You also do it from the right, which then gives you the limit itself, which then means you have to check the y value. So, I want to be neat, so let me use a line. You're physically checking 1, 2, 3, 4 things. Those are the 4 things you're checking. You just want to make sure that they have to be, every single one has to be the same. If you're proving continuity, I will look for the fact that you tried to prove all 4 things. If you're telling me the limit doesn't exist, I better see why it didn't exist. Okay? So the limit from the left, I would be using the absolute value of 2 minus 1, which is 1. Don't forget that you have to take an absolute value. What does that do to a number? It just makes it positive. Don't forget to do that piece. Some of you just make them go away because you don't like them. Makes sense? But you have to do something with them. Right side. Right side, we're going to the value of 2. 2, we would get -2 over 7. I use the top function, right? So, therefore, given these two things that are not the same, then this guy, the limit at c, does not exist. In the real world, you would stop, automatically tell me, limit doesn't exist, can't be continuous. That is a statement you can always write. If the limit doesn't exist, you can't be continuous. Because this is notes, I do want to just finish off to say, how do I find the value? You look for the equal sign. That's how you know which one's the value. Therefore, the answer to this guy is 1. Okay? That's how you find the value. Other question you guys got? No, wrong way. You also got, oh, actually, going back. I could ask you another question. Better question to start off. Where are your discontinuities? That would have been the better question for this guy. Where are your discontinuities? Samiza? Good job. I hid the infinite in there. There's an infinite at -5. Can't remove it. Can't do anything to it. But there is also what type of discontinuity? A jump discontinuity because of these guys. But I hid an infinite inside of there. Still there. So if I asked you where are the discontinuities, don't get fooled into thinking you only check this. You got to look at the functions also. Got to look at them separately and make sure there's nothing extra hiding. Okay? Think of the tricky things that I think about when I make tests. All right. Finding A. Because I do things like this, right? And I'll say, oh, well, I want the function to be continuous at... Well, actually, I could just say, I want it to be continuous, period. I just want the whole function to be beautifully continuous. What are the only ways I can make this beautifully continuous? Well, ax squared, that function, is there any issue with continuity? I can draw from left to right and never have to pick up my pen. Parabola, right? This guy is another parabola. Any issues with continuity? Any discontinuities in a parabola ever? No. Okay. So I don't worry about that. This is the only place I could have them. Right? So I want to make A. I want a value. Therefore, I will be continuous. Steps? Right? We got these two graphs and they're floating in the air. And how do I make them actually physically connect? Nick? Alright, so you got piece 1, piece 2. The only way to make them the same y value is if they are equal y values. Does that make sense to everyone? So does it make sense to everyone that step 1, I am physically going to take the left side of the function, make it equal to the y value of the right side of the function, but I want to do it at x equal to 2. And if I say that at x equal to 2, then it makes sense to you guys. What do I do with the 2? Substitute it in. Does that make sense? All right. Then you can solve it, right? Give me 1 second. All right. Continuity, IVT. IVT, so we're still in 2.3. IVT. If I asked you to prove IVT or show IVT, any of those things, that's one type of question. Other things were like the multiple choice question you got today, which was you didn't know necessarily that it was IVT. Common sense will get you the answer, but that's where it's coming from. It comes from IVT. All right? So what does IVT say? I'm going to just draw some points. Point A is here. Point B is here. If I was to physically draw a box, and I'll do it a little bit differently that we did in class. Do you see all the y values in between those two y values? Wherever those points may be, I am guaranteed all of these y values if IVT works. That's what it guarantees. Every y value from point A to point B. Okay, if point A is at -5 and point B is at -10, then I have every single y value guaranteed. How are they guaranteed? How will it possibly happen? Well, number one, the function has to be closed. Sometimes that means you have to check the domain. Number two, has to be continuous on the closed interval. That means check for discontinuities. What is that the same exact thing as? Checking for your domain. Pretty much the same. Alright. The only thing that I can think of in there would be like if there's a jump discontinuity, something weird like that. Third thing, once those two are true, then you have to find the y values of your function. Fourth thing, check if y value, or sorry, check if f of c, I'll write it with that notation, is within y values, f of a to f of b, and then if so, then IVT holds. I'm going to go to the right. That's the left, I meant. If so, then IVT holds. Find C within A to B. Those are the steps. Why do I make you do steps? You can go in a different order. You can go out of order, but you have to make sure all of it's there. Why? Because a theorem's specific. A theorem says you have to be closed. You have to be continuous. We're only guaranteeing the y values within A to B. So I'll put of A and B right there for you. Okay? Only guaranteeing those. I don't care about anything bigger than B, less than A. I don't care about those. I only care about the ones that are at the end point. And then, when I check, I have to make sure the one that they're asking me about is within there. Because let's say the points are at 2, 5, and the next point is at 10, 15, and they say, oh, guarantee me f of c is equal to 0. Guarantee me that there's zeros. Will that be in that red box of y values? No. So, step 4, not true, and I'm done. I don't have to go any further. If it's true, then yes, you have to find your c value, but only if 1 through 4 worked. A lot of you go through the step of finding the c value, but you actually never proved if it was true or not. Okay? Does that make sense? Okay? Give me a second, I gotta think about this. Alright, so I gave you the function, I gave you the interval, and I asked you to prove if IVT holds for the y value of -1. So, let's pretend you don't listen to my rules at all and you do this. Right? So you're going to solve for your y value right away. So that's one mistake. That f of c is a y value, not an x value. Some of you keep saying put it into the domain or put it in for x. You're not putting it in for x, you're putting it in for y. So multiply to the other side. I'm going to distribute my negative right away. That's negative x. I'm going to distribute my negative right away. That's positive 2 equals x plus 1. I'm going to move these over to make them positive. I'm going to move this over, which I get 1, and I get x equals 1/2. So did I find a value where the y is negative 1? Did I do it properly? I hope so. Did I find a value where my y value is -1? So at the point 1/2, my y value is -1. Did I prove that? Did it happen on the graph? 100% it did. I guarantee you if you go and graph it, or you go into your calculator and you look at x equal to 1/2, I guarantee you the y value is -1. Substitute it in. As long as I did my math right, it is literally -1. So what went wrong? I don't care that it's not continuous. Where do I care about continuity? Where do I care about the continuity? Only where they ask me to care about it. That's the only place I care about it. But what's happening inside of there? What happens at x equal to 2? Infinite discontinuity, therefore IVT can't hold. You just got this whole problem wrong by doing all this work because you didn't go and check. I need you to understand this. There's an infinite discontinuity. Okay? It's within the domain that they're telling me to care about. What that means now is, as a result, it's not continuous on 0 to 5. It's not. Guaranteed it's not. Closed? Yes. But it's not continuous. I can't finish it. But let's talk about what actually happened. Is there truly a point where a y value is -1? We already talked about it. Is there a point on the graph? Yes, 100%. I'm guaranteeing that. Graph it. Look at the table. It's there. What happened? It wasn't guaranteed. Could it happen? Yes, but you're not guaranteed it. It's like your grades. Am I guaranteeing every single one of you are going to get an A? I've never said that. I cannot guarantee it. Could it happen? Could it actually happen that, by chance, this is a great class and everyone gets A's? Could. But I'm not guaranteeing it. Or same way as I say, can I guarantee there will be exactly 5 A's in this class? I can't guarantee it. But could there? Could there magically at one point just perfectly be 5 kids with A's? Yes. Do you understand the difference between it happening by chance versus a guarantee? This was not guaranteed and it happened by chance. A guarantee means, regardless of the function itself, I know for a fact that any function with the same criteria would work. And the criteria are 2 points. That's the criteria. 2 endpoints. That's it. Okay? Does that answer your question? You had your hand kind of going up and down. From 3 to 5, yes, IVT would hold if the interval was 3 to 5 because it's outside of the vertical asymptote. Then the next question, so let's do that because I think that's a pretty good question too. So, same function. What was the bottom? X minus 2. And then we're doing 3 to 5. And then f of c equals -1. No, that's not what I meant. There we go. Was it -1? I think I picked -1, right? Okay, so let's do it the real way. Number 1, check for, I don't care, continuity or close, whichever one happens first. I don't really care. So continuity, I'm looking for discontinuities. I have a discontinuity at x equal to 2. But 2 is not within here, so I'm still good because it's continuous on the closed interval of 3 to 5. That's why that's okay. Third thing, I got to check my y values. So I got to do f of 3. 3 is 4 over 1. F of 5 would be 6 over 3, which is 2. Step 4, check if my y value, which is -1, is in between those. Is it? Which y values are now guaranteed by this function and the stipulations? From 2 to 4. Everything in between it. I could answer all of them, but I can't answer this one because it's not guaranteed. Okay? Does that make sense? Could it happen? Yeah, it could. It might, but I'm not guaranteed, and that's what I'm asking you guys, is if IVT guarantees it. Isaiah? Yes, this is your x. I put it into the function, therefore 4 is the y value. Good? All right, Douglas? Same way I continued before. How do you find the x value to match a y value? You take the y value, substitute it in, right? Then you solve for your x value. So now I'm not giving you the x's, I'm giving you the y's. so you're solving for your x's. Does that make sense? Okay, cool. All right, IVT. 2.4. All right. Average rate of change is equal to slope between 2 points, which is equal to this beautiful formula here that I'm about to put up, f of b. Whoa, did that really happen? Oh, my pen is crazy. Hold on, guys. F of b minus f of a all over b minus a. What's that the same as? Y2 minus y1 all over x2 minus x1. You'll see me use the f of b notation more. Okay? It just means y and y. Okay? So, average rate of change just means plain old slope. Rise over run. Okay? Instantaneous rate of change is the one that you guys are going to have to do a little bit more often. So, instantaneous rate of change is the same thing as the tangent. Oh, I should write the word slope first so it makes grammatical sense. Slope of the curve, slope of the tangent line. And what's key about this one is at 1 point. Those are all vocab words you know. These are all things that you should have seen. These are all the things that better go into your foldables. Limit, as h goes to 0, of f of x plus h minus f of x all over h. Or you can use a's, either way. Either one works. Okay? What does this end up giving you? Physically gives you slopes. So we'll use it in a second. I'll show you the different types of functions that I use with this formula. You actually have seen them all by now. You'll see me use any kind of polynomial. X squareds, x cubes. X cubed is a big pain in the butt. Okay? They are a big pain, because if you put x plus a into the function and you cube it, what do you have to do? X plus h times x plus h times x plus h, and you have to FOIL out that many times. It's a pain. The other kinds of functions you've seen square roots. You've seen 1 over x, 2 over x, 1 over x squared. You've seen all of those. Okay? You won't see sine and cosine yet. We don't tend to do those right now because then I have to go back to sum and difference formulas, and I don't really feel like going over those. All right, so those are probably the type that you're really going to see the most. So let's do an example. What would I ask you? I would ask you, all right, so given this function, which one do you want to do? A polynomial, a square root, or a fraction? Square root? Okay. So let's do the square root of 2 minus, and I won't make it too bad, 2 minus x. Random one. I could have done 2x. I could do x plus 5, whatever. All right, so given this function, I would like for you to find the slope of tangent line at x equal to 1. Okay? So that's what I want in the end. So, major pieces. If you see the word slope of the tangent line, then you better right away start with a limit as h goes to 0 of f of x plus h minus f of x all over h. That better be where you start when you see slope of the tangent line. Okay? And once I see that, I know that up here, off to the side, I'm going to find f of x plus h. And that would be the square root of 2 minus x plus h, parentheses, please. Let's simplify it now so that you don't have to keep writing them. Do you guys notice how important those tiny little minus signs are? your whole problem's wrong. Everything will be wrong if you forget a tiny little minus sign. So these parentheses that I have here are huge. Without them, you get the problem wrong. Okay? All right, so there we go. Equals, so this piece right here is this right here. So the square root, oh, see, what did I forget in the beginning? Limit as h goes to 0. All right, the square root of 2 minus x minus h. That's just the f of x plus h minus this piece right here is the original function here. Have I lost anyone at that moment? Two things I'm substituting in. Okay. Square root of 2 minus x. All right? And then the whole thing is divided by h. All right. So it's a limit. So I always ask the same questions. It's a limit to a value. So you always substitute first. Substitute in the 0, doesn't work. Second thing would be factor. We learned today, making sure we understand, not factorable. Therefore, step 3, simplifying. This is what we did in class today. We talked about multiplying by its, quote, conjugate, right? So, multiply by 2 minus h minus x minus h plus the root of 2 minus x, all over the same thing. 2 minus x minus h plus root of 2 minus x. They have to be exactly the same because they have to be able to cancel like we did nothing. We're simplifying to make things look different. They can't actually be different, okay? So this should still cancel. All right, now that that's done, I'm going to change my color and I'll put it back up. There you go. Now that that's done, I'm going to write my little rule under here that I'm using. A in blue minus B in red times in orange a plus b. We're going to end up using the rule a squared minus b squared. So here we go. The limit as h goes to 0. A would be this guy, and I'm going to do it in one step, but this guy squared. Does it make sense why I magically never have roots left when I do this? Right? Root and square, they cancel each other. So I'm going to do that in one step. Did I lose anyone there? I did. Root of 9. And then square it. Good. All right. Therefore, I don't need the root, which I forgot to erase. I'm going to rewrite it. Here we go. So, does it make sense now that in blue, that simplifies? Because I'm going to square it just to this piece. I'll even leave it in parentheses for you. In the red, because this piece right here, that's the B. I'm going to square it. Does it make sense that I'll end up with this? Other things I need you to understand about it, that's the same thing as you saying this one multiplied by this. First, what do you guys do? FOIL, right? First, outer, inner, last. I don't do that, so that's why I had to think about it. If you do that, it still gives you the same exact thing. It still gives you exactly what I wrote in black. Okay? I'm just taking the shortcut. I like the shortcut. Does everyone understand this rule in black and how I used it? Okay. All over h times the root of the ugly orange at the bottom. Does everyone understand why the roots are still there at the bottom? Because the bottom I took and multiplied them by h, there was nothing to cancel them. Okay? Joseph, you're good for the numerator? You understand it? All right, awesome. So then I'm just going to do my simplifying. Let's take a look. The minus here, let's distribute it so that you can look at it properly. It's minus 2 plus x. Okay? So what do we get? This 2 and this 2 cancel. This x and this x cancel. So I'm going to show all my steps so that you have it. Negative h over h. And I'm just going to write this cheating way so we save a little space. Okay? Does that make sense, everyone? Does it now make sense that I'm going to cancel my h's? And when I do that, I have a negative 1 left over in the numerator? Does it now make sense I'm going to physically do my limit? Which means that that h that was inside of here, what happens to my h? Where am I taking the limit to? To 0. So does it make sense that that just goes to 0? You have root of 2 minus x plus the root of 2 minus x. Well, what do you have on the bottom? 2 of the root of 2 minus x. What did I find? The equation for the slopes. That's all I found. What was my original question, though? I asked you where to find it. Where? When x equals 1. So how do I find the slope when x equals 1? The slope was equal to negative 1 over 2 square root of 2 minus x at x equal to 1? Negative 1? I can't remember. 1. Okay. So what's the slope then? It's equal to negative 1 over 2 root 1, which is negative 1/2. What do you think I would ask really about the question? I would ask, find me the slope. What else I would ask? Tangent line equation. How do I find that? Y minus y1 equals m times x minus x1. What do I have so far? Do I have a slope? Are we good with that? If I do, how much is it? Why are you guys so quiet? Negative 1/2. All right. Do I have a x value? Did I know where I was doing this at? Where was I doing it? At 1. What am I missing then? My y value. How do I find the y value? Substitute back into where? Do I substitute back into here where it says slope? No, I substitute back into the original, which was 2 minus x. So what was the y value? The root of 1, which is 1, and that is the number in red that goes here. So there's the equation of your tangent line. But I could also ask the equation of the normal line, right? Not much harder. Let me take this over. All right, so there's my tangent line. How do you find the normal? You have to do all of it. You have to do every single thing you did a second ago. What's the only difference? You get to leave the y value, you get to leave the x value, but you got to change the slope. And how do I change the slope? Opposite. It was negative, now it's positive. Reciprocal, flip the fraction. That's everything. If you've been here for 2 days, I just went through every single thing you learned in chapter 2. From day 1, just went through every single thing. All right. Anything left? Any questions? Anything? Thank you for being here.